we are going to talk about, in addition to naive search, what can we do with the development of reasoning engines and LLM. Yeah, so we are not going to just talk about the traditional RAG. We are going to talk about more things about recent development and recent involvement. Okay, so I think so in the first part, we are going to talk about the reality check, why your first RAG demo failed. And we know the promise of RAG. It is called retrieval augmented generation. And it was supposed to be the magic bullet. It promised to give large language models access to your private data, your emails, your documents, your databases without expensive retraining. And it was supposed to be the bridge between the static intelligence and the dynamic knowledge. So let's take a look at the naive RAG pipeline, which you know very well. Most tutorials teach you a simple recipe. You just need to chop the PDF into chunks, and you need to use some API or embedding module to turn chunks into vectors, and then you need to save this the chunks and the layer corresponding vectors and save them, and then you can perform search and use that. You can perform search during the inference time and incorporate with users' question and retrieve the chunks to answer. It works perfectly, but for only 5-page demo. But in production, it collapses. When you scale from 5 documents to 50,000 naive RAG fails, users ask, what are the safety protocols? And the system returns, safety is important because it retrieves something from generic marketing text, and it misses the actual PDF titled 2024 Safety Manual Section 5. So then we are going to talk about the 3 deadly signs of naive RAG. First, it has low precision. The retrieval, which is called retrieval trap, it finds text that looks similar but means something different. The second deadly sign is low recall, which also referred to as the missing needle. It fails to find the specific fact because the user used a different keyword. The third is hallucination. When the retrieval fails, the LLM politely makes things up to fill the gap. So if you want to know more, you can read the reference here. Okay, so today we build a production-grade system. We will dismantle the RAG pipeline and rebuild it piece by piece, use state-of-the-art methodologies. Crucially, we will also discuss how to adapt these techniques for traditional Chinese environments, which presents unique challenges. So in part 2, we are going to talk about advanced indexing, it all starts with data structure. So let's look at the flow of fixed size chunking. Standard practice is to slice text every 512 tokens. Imagine reading a book where every page is ripped in half. You lose the context. A sentence like, therefore, we must deny the request is meaningless if the previous chunk contained the reason. So let's see if there is a solution. So solution one is proposed by some scholar in 2023. They call it parent document retrieval, or small to big. The concept is that they decouple the search unit from the generation unit. So for index, they use tiny chunks. For example, a single sentence. These are laser precise for searching. And for retrieval, when a match is found, we don't return the sentence. We return the parent chunk wrapping the sentence. That is the surrounding 500 words. Why do we do that? Because we want to achieve the effect, precision in search, context for the LLM. So like we just use any one sentence in the page as for compare to the query, but when we match, we return the whole page. Solution two is hierarchical indexing. This method is called Raptor, which is a name of one NBA team. What if the user asks a high-level question like, how did the company's strategy change over 2023? A standard rag searches for keywords like strategy, finding random snippets. It cannot see the big picture. And the Raptor solves this by building a tree. So how Raptor works? Firstly, it groups related text chunks together. We call it cluster. Then it uses LM to write a summary of that cluster. We call it summarize. Then it clusters the summaries, creating a high-level summary. It repeats this action. So when you search, you can traverse this tree, finding answers at the right level of abstraction. So it is actually like a bottom-up fashion from the small pieces of information to the middle to the broad. So any label can be matched. If a user asks a more abstractive question, then it matches the top label. And if the user mentions some middle level term, it matches the middle. And if the user asks some question using specific terms, it matches the bottom level. So I think this idea is very intuitive, right? Like you make index in every level. So if you feel interested in the details, you can see the ICLR. You can look at their ICLR paper here, published in 2024. Then we are going to talk about the third solution, which is called multi-representation indexing. Documents are not just text. They have tables, they have images, and embedding a CSV table as raw text usually result in garbage vectors. So how do we fix it? We can use an LM to write a textual summary of that table. So this way is to try to convert the table into some meaningful text summary, because no one will query will write like I want to know. No one will write a query like NVIDIA 200. They will ask like I want to please tell me the average price of NVIDIA in these 5 days. Yeah, so they need a summary. So creating a summary text is more easy. It's more easy to be matched by with users query. So we index the summary for searching. We store the raw table for the answer generation. Yeah, so this solution is also treat retrieval and answer or retrieval and the generation as different stage, and they need different information. Okay, so now we are enter into the third part. We call it pre-retrieval optimization. We are going to think about some way of fixing the user's intent. Users are bad at searching. We all know that. Users type things like perfect project value reasons, and the document says post-mortem analysis of Q3 issue execution impediments. There is zero keyword overlap. A vector search might struggle to connect this. So we actually need some technique called query transformation. So yeah, users just are trained to be too good at the search. Users are trained to be to get used to use search engines, so they may like to type like 2 or 3 keywords, but these two or 3 keywords is very hard to match the real piece of information. So the technique is called HIDE. Its long form is hypothetical document embeddings. This is a psychological trick for AI. Instead of searching for the question, we search for the answer. So we firstly ask an LM to write a fake hypothetical answer to the user's question. So even the LM doesn't know the answer, it will always generate an answer, right? And this answer, although this answer is not good, it's not correct, may be wrong, but it is more easy to use this generation text to match the real answer. So then we vectorize the fake answer. We vectorize the fake answer. Then we are going to find real documents that look like the fake answer. So we can see that the query and the answer is actually has some gap, right? They actually have some gap, but the fake answer and the correct answer, they just have maybe slight difference. They may have the same sentence structure. They may just differ in the numbers or entities referred to in the statements. Yeah, so that's why HIDE works in some cases. And this idea was proposed in 2022, even before the appearance of ChatGPT. Okay, So so then we have another way to save the user. We call it query expansion, and this is a this is a technique with long history from the beginning of the retrieval field. So one query is rarely enough. If a user asks how to fix code error 500, we can ask the LM to generate synonyms such as server internal error troubleshooting or HTTP 500 debugging steps. We execute all these searches simultaneously and pull the result, and this maximizes recall. And so what do we do? What can we do before the era of LM to generate synonyms? At that time, we actually rely on dictionary like WordNet, because WordNet they compile a list of synonyms for every word. But the weakness of WordNet is that we sometimes we don't need we need phrasal synonyms, not just word synonyms, but WordNet only records word synonyms. So a phrase is like if I want to say another way for debugging steps, it's a phrase, right? So WordNet don't contain this kind of doesn't contain this kind of information. But you are very lucky because you live in LM era, so you can use LM to generate synonyms. And this synonym generation is used to be the most difficult part of query expansion, but now it becomes the easiest because you have LM. So you are lucky generation. Okay, so another technique is called step back prompting. Sometimes the details distract the retriever. For example, user may ask, what was the specific physics used in the 2004 Ferrari engine? This is too specific. And this Sunday, we just saw the F1 game in Abu Dhabi, right? And the step back method generates an abstract query. What are the principles of internal combustion engines? And it retrieves context for both the specific and the general topic to ground the answer. Yeah, so if the actually retrieval is very difficult because sometimes the answer is in the label, in the button label, and or the relevant information is mentioned is described in the button label, but the user query is in the middle label, so it cannot match. And sometimes the user's question is in the button label, and the real information is in a higher level, so they still cannot match. Yeah. So step back is used to save the too detailed query. Okay, so let's enter into the fourth part, the retrieval engine. So we are going to talk about hybrid search. We are going to mention a little about traditional Chinese optimization. And I think although many of you are not work for traditional Chinese, your mother language may be Vietnamese, your mother language may be Thai or Indonesian, but maybe you still need to face this problem, because we are not as our resource is not as plentiful as English, so we need to work on some tricks to make reg can be used in our language. Yeah, so let's talk about the myth of vector only. So vectors are great for concepts, but they are terrible at exact names or serial numbers or acronyms. For example, for this, if we go back to old school keyword search, such as BM25, is actually superior. BM25 is regarded as an out-of-date technique, but it is widely adopted in the commercialized product. Okay, so how about we combine the old SOTA and new SOTA? So it runs two searches in parallel. We firstly catch, we can use BM25 or called sparse to catch the keywords. We can use vector or called dense to catch the meaning. So then we can fuse the results using reciprocal rank fusion, shortened as RF. So the formula is here. Yeah, I'm so surprised that many of my master students in my lab don't know this formula. They just use weighted sum. But I think you can try this score, because this is widely used in the IR community. And if you write a paper or write your thesis without mentioning RF, the IR community will treat you not doing enough literature review, because you just overlook this widely adopted standard. So all these techniques are not new. They are mentioned at some time, but because your training is from the deep learning era, so you forget all of them. But sometimes you need to pick them back. Yeah, and you need to go back to at that time to read those papers. Okay, so now we are going to talk about the challenge brought by traditional Chinese. Firstly, is we need to deal with tokenization. In Chinese, characters runs together. Standard models often chop Chinese incorrectly. So, for example, if we input 台北市长 translated as mayor of Taipei, the bad speed is like Taipei and 市长, but it's still okay because it's not too bad. Yeah, it just not treat the whole Taipei 市长 as one entity. And there is even worse speed like Tai and 北市 and 长. So this causes a phenomena called semantic drift. Yeah, because if we split it into 台北市 and 长, that means that 北市长 and it means like Taipei City grows, but actually the original meaning does not have has nothing to do with growth, right? So we can use models trained with sentence piece or specialized Chinese tokenizers. And that tokenization is very important for large language model and the RAG. And another challenge brought by traditional Chinese is the model gap. Many top models were trained primarily on English. They understand Chinese, but their culture nuance is translated. So we need models that are native to the language structure. Okay, so currently the strongest open source contender for Chinese reg is unfortunately made by China, BGEM3 from BAI. Why I say unfortunately, because it is, I don't have any political bias, but I just say that it is not allowed. It is not allowed to use in Taiwan. Yeah, so it is prohibit to be used in any Taiwanese system. If you want to open it to the public, then this is not allowed. Yeah. So why M3 is the best, but then I need to introduce it because it is designed as multilinguality and multifunctionality and multi-granularity, and it has the longest context among all open source embedding models supporting Chinese. Yeah, so if you are English speakers, you have other choices. But if you are Chinese speakers, if we are going to develop Chinese reg system, you have very few choices. Yeah, that's the reality. And its context is a 8,000, around 8,000. So it can embed very long documents. And that is important for reg because reg need to index all chunks. And I think the best one for MPG M3 is that it is hybrid native. It outputs both dense vectors and sparse weights in one go. So if you are interested in that, you can take a look at this reference. Okay, in part 5, we're going to talk about post retrieval. So retrieval is dirty. Even with hybrid search, the top 50 results will contain garbage. If you feed 50 documents into an LLM, it gets slow, it gets expensive because it consumes more tokens. It that your LLM need to read more tokens, like 50 chunks, and it gets confused because both the relevant information and the irrelevant information mix up. So the model will maybe combine some of them and generate hallucination. So actually, we need a filter because embedding is not a reliable matching. It significantly condense the information contained in like 500 tokens into one vector. Which loses a lot of information.